It didn't say it's recording. So let me just make sure it is recording. Say recording, okay. Did not give me the warning that it's recording. All right, so welcome to Math 349, Operations of Order. So what I want to do today is, continue to give you a sense of, possible topics that you can explore in greater detail. I've emailed you about just a small writing assignment just to start, the work on that. But I really want to give you an opportunity to see the different possibilities before you really start investing a lot of time. We have an entire semester. There's no reason to force you to choose things quickly. So the writing will pick up a little bit later. What I want to do is continue to talk about how do we come up with interesting examples? How do we come up with ways of attacking problems and writing problems? So one of the biggest issues people often have is they forget what conditions are needed to justify things. And a lot of times it's really not a big deal because it can be justified. But every now and then there are situations where something seems reasonable, but there are strange counterexamples where things fail. So we talked last time about integrating a limit versus the limit of an integral. And we saw that if we could go off to infinity, we could come up with counterexamples. If we confined ourselves to a bounded interval of 0, 1, we could come up with a counterexample if the function got arbitrarily large. And so we can't just cavalierly interchange operations. We can't just do whatever we want. We have to have justifications. And then we suggested at the end of the class that maybe if you assume that the function is bounded, that might be enough. And that actually will be enough. If your function is continuous and bounded, then you can say the integral of the limit is the limit of the integral. And that's a nice exercise to write that up carefully. What I want to do today is something my physics mentor showed me my freshman year before Thanksgiving, so we would have something to talk about over the Thanksgiving table. I think he greatly overestimated how much interest there would be in my table to stuff like this because most people in my family are engineers. But I want you to try to solve the following problem for me. So we're going to define the integral on a function f by integral of f means integrate from 0 to x of f of t dt. Okay, so I'm just defining the integral sign to just mean take this function f, integrate it from 0 to x. Okay, and I want to find all f such that the integral of f equals f of x minus 1. Anybody have any thoughts about a function that might work? So I want the integral of my function to be my function minus 1. Any thoughts about what function might have a role to play in this? What notation do you normally use for the integral of a function? If I give you the integral of f, how would you normally write its integral? What notation do we use? You've done this in Calc 1 and Calc 2. If I give you a function little f, what notation do you use for its integral? So large f. So maybe let big F prime equal little f. So the integral of little f is the integral from 0 to x of f of t dt. So that's big F of x minus big F of 0. Want this to be equal to little f of x minus 1. Or if you want, big F of x minus f of 0 equals big F prime of x minus 1. So any thoughts about what function might work? Can you think of any other way maybe you want to group these terms? I've got your big F of x minus big F of 0. I've got big F prime of x minus 1. Any other way you might want to group the terms? Okay, I'm going to do it the other way, but I'll do F of x minus F prime of x. Put all the x's on one side and put all the non-x's on the other side. So we've defined the integral symbol to mean integrate little f from 0 to x. We're trying to solve integral of f equals f of x minus 1. And so, just standard calc notation, let big F prime be little f. And when we do this now, what do we notice about the left-hand side? What do we notice about the right-hand side as I vary x? So what do you notice about what happens as we vary x? What must be true about the right-hand side? It's constant. So this is constant. So what must be true about this side? Well, if this equality is supposed to hold and the right-hand side is constant, what must be true about the left-hand side? Has to be constant. There's no other way we can have this. So again, when you're trying to teach, when you're trying to lecture, when you're trying to write, you want to think about how should I present the material? What do I want to emphasize? How do we attack a problem? So when I look at this and I see this line, integral of f is equal to f, I'm trying to think of a function that's related in a very nice way to its integral. Or conversely, a function that's related in a very nice way to its derivative. I'm somehow getting it back. So if big F is equal to essentially big F prime up to a constant, what should we think of for big F? Yeah, it looks like this should probably be e to the x. If you think about what's going on, if I change the value of big F by a constant, is that going to change things? Well, it could, because if I add a constant to it, then over here, that constant vanishes. So I can't just play games and just throw away the constant. So I'm trying to solve now big F of x minus F prime of x equals a constant. What would be the nicest constant to have? 0. And so if I choose maybe f of 0 to be 1, then that's going to make the constant very nice. And so what I would get is, I would get f of x is equal to e to the x plus f of 0 minus 1 times x. And now when I take the derivative of that, I will just get f of 0 minus 1. So what would be a really nice choice? So it's very simple. If big F of 0 equals 1, then we get big F of x is just e to the x. So for a problem like this, it might look very difficult at first, in terms of how do we attack something like this? How can we find a way to approach something like this? And so one of the things you want to think about is, how can I rewrite this? What are the different ways? And for some people, one way is going to look easier, is going to resonate more than another. And so as a professor, I'm trying to look at the class and say, okay, which way seems to make a connection with someone? Does this way work? So for me, as soon as I see integral of f equals f, I'm thinking the exponential function. Because when I integrate my function, I get my function back. Which function essentially keeps its form when you integrate it? The exponential. Or if you want to look at it the other way, if I take the derivative, I'm basically getting back to where I started. I'm thinking of the exponential function. And so if you had just tried e to the x by divine inspiration, you would see that works. So is everybody comfortable that e to the x solves this equation? All right, let's do it another way. So we define the integral of f to be the integral from 0 to 1 of f of t dt, and we want to solve integral of f equals f of x minus 1. Okay, so it's the same as f of x minus the integral of f equals 1. Yes, I've just subtracted. So this is the same as 1 minus the integral acting on f equals 1. Right? So 1 minus integral inverse times 1 minus integral inverse, I'm sorry, time acting on f equals 1 minus integral inverse acting on 1. Well, what's 1 minus integral acting on 1 minus integral? What does that equal? I do 1 minus integral, and then I invert it. It's just 1. So the left-hand side is just f, and the right-hand side is 1 minus integral. Well, that's just 1 plus integral plus integral integral plus integral 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 plus dot dot dot. What am I using? So I claim 1 minus integral inverse is 1 plus integral plus integral integral plus dot 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 dot. Why is that true? Have you seen anything like this? We've mentioned it in the class. Any thoughts? Where have we seen something like this? So one of the hardest things is if I use certain letters, then you'll know what it is. Geometric series, right? What is R? Yeah, did you know that the geometric series also works when you replace R with the integral operator that we've just defined? So let's keep expanding and see what we get. So this would be 1 acting on 1 plus the integral acting on 1 plus the integral acting on the integral acting on 1 plus the integral acting on the integral acting on the integral of 1, and so on and so on. All right, 1 times 1 is 1. Somebody tell me, what is the integral of 1 with our definition of what the integral symbol means? Yes. Why 1? So we're taking the function to be 1, and then we're integrating it from 0. Oh, shoot. I have a typo here. So your answer is correct, but I wrote the wrong thing from the previous page. This was defined to be x, not 1. Sorry. Yes, so if I actually write the right thing, you would get x. Because we just integrate the function 1. What function has derivative 1? It's x. We evaluated it. I'm sorry, we're integrating the function f of t, so we're integrating t. It's antiderivative. I'm sorry. Take 3. Take the function 1. Integrate it with respect to t, we get the function t. We evaluated x and 0, we just get x. We now know that the integral of 1, this is just going to equal x. And so using our notation, this would then become the function t. What do we get when we integrate the function t now? You could say 1/2 x squared. You could say something else instead of 1/2 x squared. You could say x squared over 2. You could say something else instead of x squared over 2. There's another way to say 2. I can always erase later. Let's look at the next one. We know the integral of 1 is going to be our function t squared over 2. What happens when you integrate t squared over 2? What function has derivative t squared over 2? T cubed over 6. Do you really want to say t cubed over 6, or do you want to rephrase it?
I guess rephrase it.
How would you rephrase the 6? Three times 2. And instead of saying 3 times 2, what could we say? Yeah, it's just 3 factorial, right? And instead of 2, we could say that is, and x, we could really write x as x over 1 factorial. And if you really wanted to, we could write this as x to the 0 over 0 factorial. What function is this? Taylor series of what function? We have 1 plus x squared over 2 factorial plus x cubed over 3 factorial. I'm sorry? This is just e to the x. That's the Taylor series for e to the x. So we showed on the previous page that the unique function that works is e to the x. And we just got that over here by expanding the operator 1 minus integral inverse as 1 plus integral plus integral integral plus integral integral integral. Is this legal? When can you use the geometric series? When can you use the geometric series formula? If I want to use the geometric series formula, what must be true? Not quite. Absolute value of r is less than 1. So if I was between 0 and 1, you can definitely do it. But you can do it in a greater generality. So the question is, what does it mean for this integral operator to be less than 1 if I want to use something like this? So if I want to write down the inverse of an operator, I want to use maybe the geometric series formula to expand out and find the inverse. This is an extremely powerful technique. In order to do this, I need to introduce a notion of the size of an operator. There is a way to make all of this justified. I learned this from a physicist. Physicists are often willing to play fast and loose with the mathematics. But you can make this rigorous. And so the reason I wanted to talk about this problem is twofold. I guess the reasons. One was, I find it just interesting, and it leads to some good theory questions as to how do we generalize something we already know? So everybody here should have taken multivariable calculus. Yes? If I give you a vector, what do you associate to a vector? Direction and magnitude. How do you denote the direction? I'm sorry, how do you denote the magnitude of a vector? Well, that's how you compute it. What notation do you use for the magnitude of a vector v? We don't use brackets. Well, the arrow on top denotes the vector. How would you denote the length of a vector? So do you use one vertical line on each side, or do you use two? How many people use two? How many people use one? Okay, so depending on which book you use, some books use two. A lot of times you use two to just highlight and emphasize to the reader, this is a vector. And so the double vertical lines is reminding you that you are working with a vector. The single line is just overloading or changing the definition of the absolute value. When you first learn the notion of an absolute value, you learn the notion of an absolute value for, I don't even know if it's real numbers. It might just be for integers, where positive and negative integers. And then you extend it to real numbers, and then you extend it to complex numbers. Well, we can continue and we can generalize the notion of absolute value to a vector and use just a single line like that. You really want to think about your notation. You want to think about what it means. For the geometric series, it's the absolute value of r is less than 1. Well, if I have a real number, that's not a problem. The question is always going to be, what can I expand this to? What can I put on in place of the integral and still have things work? And so, for the operations of order book, which I think is going to be a fun book to write, it's trying to take a lot of things you've seen and ask, how far can you push them? So we should probably start talking about things where order matters. So we've already seen an example with the limit of the integral and the integral of the limit. When you think of math operations where the order matters, if your first thought is limits of integrals and integrals of limits, you need help. And we have wonderful counseling services both in the department and the college as a whole. So if this is your default, we're here for you. Okay. If you go and talk to young kids, this should not be your default of math operations where order matters. Can somebody give me a default order matters? Subtraction, right? So so 326 plus 512 is 838. But what if I gave you 512 plus 326? What does that equal? Good, also. And it's great that you use the word also, because addition is commutative. Once I've done the first problem, there's no work to do the second. If I give you, I'm not brave enough to do a subtraction. This is public. If I gave you 8 minus 2, that's 6. Very different than 2 minus 8, which is negative 6. So our default for something where order matters is subtraction. After subtraction, what would you go to next? Division. So division matters. And if we're doing the product rule, is there really a difference between the product rule for f times g or g times f? No. But f over g and g over f, very different. All right, so division matters. Now, what would you do beyond that? What's the next thing you might choose where order matters? That you might have seen. I'm sorry? Exponentiation. So what would you do for that? Give me an example. How order matters, yes. Okay, so if you do like that, changing in terms of where they are. But what if I gave you 2 to the a to the b versus 2 to the b to the a? Does that matter? So what's 2 to the a to the b? This is 2ab. And what's 2 to the b to the a? So they're both 2 to the ab. So here order doesn't matter. If I give you, yes, if I change which one is where, that will matter. But if I look at an exponentiation too, like that, which would you rather have? A shirt marked up 20%, then discounted 10% versus discounted 10%, then marked up 20%. Quick thinking, who would rather have, I take off 20% first, and then, I'm sorry, raise it 20%, then discount 10, or I discount 10 and then raise it 20? How many people would rather have the first? They're the same. So in the first case, it would be, if X is the price, I want to mark it up by 20%, so it's 1.2, and then I discount by 90, by 10%, so I multiply by 0.9. The other one, I first discount by 90%, and then I mark up 20%. There's no difference. Which do you think you're more likely to see in a store? Yes. The top one. We've got something on sale. Right? It looks like this is a deal. How many times have you been in a store and something seems like Oh, I want to get this, it's on sale now. Makes no difference. They mark up the price, or they might mark up the prices first and then display it like this. How many of you have ever bought a combo package? We have a special hamburger, soda, and fries. How many of you have checked to make sure that it is cheaper to get the combo package than the three? Have you ever been in a situation where it is actually more expensive to get the combo package? There are a lot of times when the combo package is more expensive than the constituents. So just things to be careful about. All right, there is a great example of something in mathematics where order matters, which you've hopefully seen going back maybe to algebra 2, maybe algebra 1. Matrices, right? So matrices is one of the default examples of order matters. And so let's look at n by n matrices. And so if I don't look at n by n matrices, order clearly matters, because if they're not square, then I can't do both A times B and B times A. How were matrices defined to you or explained to you? There's a lot of ways to view matrices. Collections of vectors. And so if you then have a matrix acting on a vector, it's going to give you a linear combination of the columns of your matrix. Sometimes you talk about a matrix as you have a system of equations and you're extracting the matrix elements. Another way of looking at a matrix is it's a transformation. You take a vector as an input, you get a vector as an output, and the matrix is going to tell you how you get from input to output. So as a Bostonian, I hate New York City, but there is one part of New York City I have to give credit to. What is that part? The grid system in Manhattan, right? If you are walking in Manhattan and you do not use the grid system, you're an idiot. Everything is beautifully aligned with the streets going north-south, east, with the avenues north-south and the streets east-west. It's very easy to get along. Boston, you have roads crossing each other in terms of sometimes, Comm Ave is north of this one, sometimes it's south, and the roads can flip. You want to choose a good coordinate system. A huge amount of linear algebra is whatever problem I give you, what is a good coordinate system to use for that problem? Sometimes the choice of coordinate system is obvious. And if you have an obvious choice of coordinate system, okay, use that. Other times, you might have a natural coordinate system that you want to use, but the problem is not well designed for. And so one of my favorite examples, and some of you might have seen this, I might have done this in operations research. If I give you an ellipse, does anybody remember what the equation of the ellipse is? So x squared plus y squared? Almost. That'd be the equation of a circle. I'm sorry? Right, so what would be the coefficients? You could also write that as x over r squared plus y over r squared equals 1. And that's now the two directions are equal. And so the more general case is x over a squared plus y over b squared equals 1. And A is going to be the semi-major, B is the semi-minor. Some books always require A to be larger than B, because there's sometimes relations also with the foci. I'm not going to go into all of this. You can write this in matrix form as a matrix acting on a vector and its transpose. And it's 1 over a squared, 0, 0, 1 over b squared equals 1. Or my vector, v transpose AV equals 1, where v equals xy. This is a nice way of writing the equation of an ellipse that is oriented with the standard axis. How many of you remember doing this, maybe high school, junior high, something like this, all the conic equations? You should never have done anything like this, where I now give you the ellipse, but it's not oriented with the coordinate axes. So there's a very easy way to do this. And the easy way you do this is you change your coordinate axes. And so in the green, we know what to do. We know how to write down the equation in the green. And then, so what you do is, let's call the green the UV space, and let's call, this the XY space. And so you can rotate, and we'll call this angle theta. So you can rotate from one to the other. And so I don't want to go through all the details. I'll leave this for you to think about. But what you can do is you can write it as UV transpose 1 over a squared 0, 0, 1 over b squared UV. And then you just have UV is some rotation matrix times XY. And then when you plug that in, at the end of the day, you'll get XY transpose. And then this new matrix theta transpose 1 over a squared 0, 0, 1 over b squared theta, and then XY. And so you can actually write down the equation of an ellipse very nicely. And it turns out that this matrix is going to be a symmetric matrix over here, 2 by 2 symmetric matrix. What I want to emphasize is that a lot of linear algebra comes down to what coordinate system do you want to look at. And for this coordinate, for this ellipse, when it's not aligned with the XY axis, you should just rotate back, theta radians. And now all of a sudden, the equation is going to be very simple and easy to write down. You're going to have a diagonal matrix again. Everything's going to be nice in UV space. Whenever you write down a matrix as a transformation, you have to specify what is the basis you're using for the inputs, what is the basis you're using for the output. And so if you think of a matrix as a transformation, depending on how you orient your axes, depending on what you choose as your basis vectors, the matrix will look very different. But it can be the same transformation. If I want to talk about, I stretch by a factor of 2 in this direction, and I stretch by a factor of, or shrink by a factor of 2 in the other direction, that's very easy to write down with my orthonormal basis there. It would be much harder to do that with the standard XY. And so a lot of times you want to figure out what is the nice way to write things down. So let's talk about, do matrices commute when we multiply? And so let's do some cases first. So matrix multiplication. Let's do n equals 1. So I have two matrices AB. Does AB equal BA? Well, I'm looking at n equals 1. So these are 1 by 1 matrices. Yes. So therefore, by induction, everything's good. Right. So what about 2 by 2? So let's try matrix multiplication. Let's do n equals 2. Okay. Can anybody give me an example of two matrices which do not commute under multiplication? Okay, what's your idea? Yep, 2 by 2.
Left to right, top to bottom.
Yep.
1, 1,
1, 1. Oops. 1, 1,
1, 0.
1, 0. And the other matrix?
1, 0, 1, 1.
Okay. So how can we tell if this is right? So just solve it. So if we actually multiply things out, we're going to get, I think, 2, 1, 1, 0. Did I do it correctly? And for the other one, we should get 1. Okay, that's already enough to know that's already enough to know that they can't be the same. Let's just bring it home. It's going to be 1, 1, 2, 1. Excellent. So how did you come up with this example?
It just felt familiar, so.
Okay. How would you come up with an example like this? So again, in mathematics, if you can give me a specific counterexample, that's enough to prove that it's not always going to hold. But how can you formalize the thought process? Why is this a natural thing to try? What's nice about these matrices? Okay, but I mean, I could do any 2 by 2 matrices. I could have done pi, e, gamma, and zeta 5. Right? Why did you choose these matrices? What's nice about these matrices? A lot of zeros and ones. So easy to try and search. So how many possible matrices are there with just zeros and ones? So if we just have zeros and ones as my entries, nothing else other than zeros and ones, how many matrices are there? 16. So how many choices are there for the 2 matrices? Why 32?
Because it's 16 for each.
Right.
16 and 16.
Okay, so one thing is, okay, but would we add them?
No,
You'd multiply. 16 times 16 is 256, I think. But we know, of course, it can't be 16 times 16. Why not? Or at least, why would I never check 16 times 16? Okay, so one thing is I could throw away the 0 matrix. But once I've chosen my first matrix, what do I know about the second matrix? Can't be the same. I'm trying to show that matrix multiplication is not commutative. So when I'm trying to find my counterexample, I'm not going to take the same matrix twice. Okay, so once I choose this matrix, there are only 15 possibilities for the second one. Now for the first one, as there are really 16 possibilities, we've already said throw away the 0 matrix. What else can you throw away? You can throw away the identity, because if you put in the identity, it's not going to change anything. What else can you throw away? All ones, because if you put in all ones, or can we throw that away? Does it matter if the all ones are on the left or all ones are on the right? Right, so then the question becomes, can exclude the identity matrix, 1, 0, 0, 1, the 0 matrix, 0, 0, 0, 0, but maybe not the matrix that's all ones. So let's explore that. So let's say we have all ones, and we want to try to see if it matters which side we put it on. I'm going to just put down a general matrix A, B, C, D. And so when I start to multiply, I'm going to get A plus C and B plus D, and then A plus C, and then B plus D. Versus now, if I do it over here, I'm going to get A plus B, and then C plus D. Yes? Have I avoided making a mistake so far? Okay, and then the next row will also be I mean, so- I'm sorry. Yeah, so it's going to be a plus b, and then it's going to be a plus b. Yes. Let's see that. Which one? There you go. And then it's going to be c plus d, c plus d. Right? Okay, and then the first one was a plus c, b plus d, a plus c. Okay, good. So can we just throw away the 1, 1, 1, 1? No. So if b does not equal c, not the same, cannot throw away the 1, 1, 1, 1 case. Again, to me, what's really important right now is the thought process. There's a lot of problems in mathematics that can be trivially solved by brute force. If I want to factor a number, can you give me an algorithm that will factor a number? I don't care how long it takes to run, I'm patient.
Yeah.
Guess and check. But you want to make sure that it's going to correctly factor it and terminate. So if I'm sorry? Good. So I could just try dividing all the way up to the number I'm looking for. Well, I can do a little bit better. I can just stop at the number 1 before. And I can do even better. I can stop at square root. But it's still going to take a tremendous amount of time. That's okay. We're patient. Over here, when we're trying to find cases, when we're trying to search for things, if we can limit the space a little bit, that's great. And now instead of looking at 16 possible choices, we've been able to throw away, when we're trying to find it, we've been able to throw away 2 things. So instead of 16, we have 14. And then for each of those 14, how many possibilities do we have? So originally, it was 16 times 15 possibles. Now it's 14 times 13. Because we're not going to use either the matrix of all zeros or the identity matrix for the second choice, and we can't use the one we just chose. So instead of 16 times 15, there's 14 times 13. So when you're trying to come up with counterexamples, you want to try to find what's an efficient way to search. So we were lucky. You got this very quickly, so you saved the class a lot of time. You can start playing games with how many zeros do you want to have? Do you want to start off with something with 3 1s, or would you want to start off with something with 3 zeros? So one of the problems is if you start off with 3 zeros, maybe none of the 1s ever hit each other, and maybe the multiplication becomes the 0 matrix. Can you come up with an example with 2 zeros and 2 1s? So as a nice exercise, maybe we will say the weight of the matrix is going to be the sum of the 1s. And so you've just given me a counterexample to matrix multiplication being commutative with a total weight of 6 from the sum of the 2 matrices. Can you do something smaller? What's the smallest you can do? What if I allow you to use negative signs as well? You can use 0, 1, negative 1, but I'll consider the weight of anything that's not 0 to be 1. Could you do something with more zeros if you allow yourself a negative 1? So sometimes it becomes interesting trying to figure out what is the most minimal example you can find. Now, it would be nice if A times B equals B times A for matrices A and B. We know that this is not going to happen. So then the question becomes, you're given A, find all B such that AB equals BA. So when are you allowed to interchange the order of operations? When are you allowed to say A times B is B times A? Who knows what this means? It's my favorite logarithm, W log. Without loss of generality. One of my friends in college once slipped and said, without loss of generality, without loss of generality. So it would be nice if we could assume certain things about one of the matrices to make the problem a little bit simpler. So if I want to try to figure out when does order commute, what would be a really nice class of matrices to study? And so maybe what we do is we start off with a simple class of matrices, understand what goes on there, and then try to expand to larger and larger and larger. Okay, this is the thought process. Don't try to do a hard problem all at once. Break the hard problem up into a lot of smaller, easier problems. For each one of them, make some progress. What would be a really nice class of matrices to study? Well, okay, so we'll do 2 by 2. Assume n equals 2. And what kind of matrix do you want to assume for A that might be really easy to look at? What's an easy type of matrix to study?
0.
I'm sorry? 0 identity. 0 and the identity are actually both special cases of a type of matrix. So they're symmetric. So there's something between symmetric and triangular, not symmetric. So if we want to have our plot, we have the 0 and the identity matrix over here. Diagonal. So here's diagonal, here's symmetric. And then triangular. So we have an inclusion like this. 0 and the identity are actually special cases of diagonal matrices, which are special cases of symmetric matrices. They're also special cases of triangular matrices. And so depending on which way you want to go, I can expand up from the 0 and the identity to diagonal to triangular or to symmetric. And so I'll leave this for you to think about over the weekend. If I want to try to prove, if I want to find all the B that compute with A, if A is either the 0 or the identity matrix, it's not going to be that bad. What about diagonal matrices? Is it going to be easy to analyze in the special case when you're diagonal? What would be true about the B's in that case? And if the diagonal case is easy, if we can actually resolve it, then we can hope maybe we can expand up to either symmetric or triangular. And if we're having trouble with the diagonal, then okay, then we need to reassess. But always try to think, what kind of properties can you put in that will make the calculations a little bit easier? And then go from there. I think it's a good place to stop.